there are a couple of very important things you can tell from a graph of displacement and the force that a spring applies. All right, in the context of spring forces. Okay, two important quantities you can take from this graph, and what those quantities are really comes from the relationship between force and displacement for a spring, and as we now know, that equation is that spring force is K times X, which is a part of what's called Hooke's law that relates these two quantities. Now, Hooke's law also talks about the direction of the force being back toward equilibrium. So sometimes you see this, when we think about the directions of things, there's a negative sign in there. But here, this graph is just for us going to talk about the strength of the force, what we call the magnitude of the force. Clean this up a touch. So that relationship, when we graph it, well, is linear. All right, you'll notice this looks a lot like y equals mx plus b, and I don't just mean because these are both x's. That's a coincidence. This is also an x, but it just happens to be what we call displacement for a spring. And you'll notice that our spring force doesn't have a term there for the plus b, which really means that b is 0, which really means that the y-intercept of this graph is 0. And yeah, that's because if a spring is not displaced at all from equilibrium, then the spring doesn't apply any force. Okay, fine. Now, I'm going to arbitrarily say that at this amount of displacement, and that displacement can either be making the spring longer or making it shorter by stretching or compressing it, I'm going to say that the force that the spring applies is that much. That happens to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 boxes up. And that's going to get me a graph that looks, hey, that's my line. Looks there, like this. Fair enough? Okay. Now, let's clean this up. Now, this also does show us, the nature of spring forces, and that is that, maybe I shouldn't have gotten rid of those things. Yeah, let's put those back. So it shows us that, if this spring, say, is stretched this much or compressed that much, the spring responds by applying that much force. And if you say, take 1/3 of that amount of displacement, well, the spring responds by applying 1/3 as much force. That's the nature of the linear relationship. By whatever factor one quantity changes, another changes by the same factor. Okay, so we cut x in 1/3, we cut the force in 1/3. If we stretch this thing 10 times as much, then the spring applies 10 times as much force. Now, things you can find from this graph. Well, you'll notice that, especially when we say these two expressions are pretty similar, right? Here's the stuff on the y-axis. Here's the stuff on the x-axis. That means that k is the slope. All right, so one big thing is that k is the slope. The spring constant k we can always find from a graph of force versus displacement by evaluating the slope. And a couple ways to know that. I mean, one is, just sort of look at how different quantities are the analogies of other quantities. Another one is, well, let's see, slope is always like a rise over a run thing. And you'll notice that the rise is measured in newtons, the x is measured in meters. So you either say, well, that tells me that k is measured in newtons per meter, or you say to yourself, well, I know that k is measured in newtons per meter, so that means I'd have to divide this by that. Oh yeah, I would do that if I was finding slope, right? Either way, that's a big takeaway, that for this graph, k is represented by the slope. Now, the other thing that you can find, the other operation you can go through when evaluating a graph, especially a graph with only straight line parts. Now, how do I grab just this stuff? Good, group it. Let's put this aside over here. The other thing you can look at is you can say, well, whoops. Is you can look at how much force is applied when this spring is displaced a certain amount. And you can say, like, for example, well, when the spring is displaced that amount, the spring applies that much force. And then, well, you can look at this area between what I call the curve. Even though that line is not curvy, you can still call it a curve. You can look at that area, because that area, if we look at this area, well, the area of that shape is 1/2 base times height. Right? It's a triangle. All right? But the base is, well, an x, and the height is a force. And, well, how big is this force, spring force? Well, according to our equation, that's 1/2 x times kx, which means this area is 1/2 kx squared. Now, maybe you recognize what that's an expression for, and or maybe you can say, well, wait a minute, I didn't talk about that this force is measured in newtons, this displacement is measured in meters, so this has units of Newton meters, meters times newtons, and that by definition is a joule. So that means that this area is measured in joules. Here's the equation that really dictates how much area that is, and that by definition is the potential energy stored in the spring when it's displaced by an amount x. All right, so not only is area 1/2 base times height, well, sure, the big deal is that area is U spring. So we've got two different quantities we can identify through some, through some mathematical operations, assuming there are like actual numbers on here, right? If these are given values and the x coordinates are given values, we could actually calculate the spring constant. We could actually calculate how much energy the spring stores. Now, when we look at what I call translating one graph to another, I want to show you something that's kind of neat. Now, we know here, right, that this is F spring is Kx. We know that this here is U spring is 1/2 Kx squared. Well, notice, let's go back to our generic, arbitrary, I should say, identification of for this much displacement, there's that much force that the spring applies. Let me get my line there. And we get that. Fine. Now, what I'm going to say is, well, remember, if we look at the area, say, of this triangle, when, here we are, when the spring is displaced this much, it responds by applying that much force, and this area, I'll call this area 1, is, I don't know, U spring 1, a certain amount of spring energy. And let's take this triangle and see if I can move it up here. Yeah, so that triangle has an area 1/2. Well, let's call this, whoops, let's call this X, and let's call this F. All right. Well, this area is 1/2 X times F. All right. So we've just defined that amount of energy. Now watch this. And let's define that as, right here, let's call this U spring 1. And we'll say at that amount of stretch or compression displacement, X, there is U spring 1. Now watch this. When we go to 2X and displace the spring that far, notice the spring responds with applying a force 2F. A force 2F. 2F. And what we have now is this triangle, where the area of that triangle, I'm going to move my 2F back. I'm going to move this. Where the area of that triangle, and let's call it A2, that's U spring 2, is 1/2 times 2X times 2F. Or that's US2 is 1/2 times 4XF. Or notice it's 4 times as big as this. So it's 4US1. Which says when we go out to 2X, we don't double the energy stored in the spring. 1, 2, 3, 4. It gets 4. So here's U2, which is 4US1. And now here's a new data point on this graph. And then when we go out to 3X, well, again, our spring responds by applying a force 3F, and then we get this triangle. And the area of that triangle, A3, is, well, U spring 3, which is 1/2 times 3X times 3F. Or U spring 3 is 1/2 of 9XF. Or it's 9 times as big as that. And so 4, 5, 6, 7, 8, 9, here's U3, which is 9US1. This is S3. And at 3X, we get 9 times the energy. And what we get now is a pattern that looks like that. A quadratic. Well, no kidding, right? Because, yeah, the equation is quadratic. The equation relating displacement and energy is quadratic. And this says by whatever factor we alter X, we don't alter U by the same factor, we alter it by that factor squared. All right, now, do you have to go through this whole idea of comparing this area and then this area and then the green area? Do we have to do that in order to justify, this relationship? Well, no, because we have the relationship, but it's sort of a chicken and egg thing. Which one do you start with? Which one do you get to? I mean, the justification for why this relationship is what it is really sort of comes from the fact that the area of these triangles has to be an energy. And that area has to be an energy because the area is measured in units of energy. All right. So it's a nice way to be able to tie together and provide proof from a couple of directions as to why these graphs look like they do, why these equations are what they are, and for us being able to interpret, the special characteristics of these graphs and what we're trying to study is important. Okay? So what I will leave you with for sure is real important to be okay with that there are two things from a single graph. Sometimes there are two things you can find. The slope is sometimes a value, and the area is sometimes a value. All right? So as it applies to a graph of spring force versus displacement, understand that those two quantities, both energy and spring constant, can be found from the same graph. Okay? Okay.